Imagine a powerful machine humming away, doing its job. Maybe it's helping your washing machine spin, maybe powering a fan, or even driving some huge factory conveyor belt.
Hmm.
How do you know if it's the right machine for that specific job, or if it's running safely, or, how long it's actually going to last?
Yeah, good questions.
Well, just like we carry ID cards, think a driver's license or passport. Every single electric motor has its own kind of secret identity. It's a vital piece of information that tells its whole story.
That's a great analogy.
Welcome to the deep dive. Today we're exploring something that's often overlooked but is honestly critically important for anyone who uses or works with electric motors.
Mm.
We're talking about the motor nameplate.
That little metal plate, usually right on the side.
Exactly. Think of it as the motor's essential ID card, tiny but packed with information. Our mission for this deep dive, especially for you, our curious listener, maybe you're new to electricity, maybe just looking to connect some dots, is to unpack this ID card.
To make sense of it all.
Yeah, and truly understand what those markings mean. We'll make it clear and easy, really break it down for beginners. So the next time you see one, you'll know exactly what you're looking at and why it matters.
Sounds good.
Our insights for this deep dive are based on understanding motor nameplates. And we're drawing from John Beelingchill's excellent book, Real Beginners, Step-by-Step Electricity, which is published by Gilbert Publishing.
A very practical resource.
So, okay, let's unpack this. We're talking about the silent guardian of every motor, providing crucial information just at a glance.
That's a perfect way to put it. If we connect this to the bigger picture, the nameplate is so much more than just a label. It really is the motor's unique identifier, like its birth certificate and its health record all rolled into one.
Birth certificate and health record, I like that.
Yeah, because this small plate carries essential characteristics.
Yeah.
And these are absolutely critical for ensuring the motor operates safely, efficiently, and importantly, lasts for a long, long time.
Right. Longevity matters.
Definitely. Without understanding what's on it, you might inadvertently misuse the motor, and that could lead to damage, a much shorter lifespan, or worst case, even a dangerous situation, like, a fire.
And it's not just printed on some flimsy sticker either, is it? You notice these things are built to last.
Exactly. To withstand really harsh conditions, think heat, dust, vibration, and to prevent discoloration or deformation over time, they're primarily made from durable materials, often stainless steel.
Right. Makes sense. They need to be tough.
They're designed to be as resilient as the motor itself. And while the specific content, the details, can vary a bit depending on the manufacturer and what the motor's for, generally nameplates include a pretty comprehensive set of details, more than you might expect sometimes. Things like its rated voltage, rated frequency, rated current, rated output.
Okay, those sound important.
They are, but also insulation class, temperature rise, even starting class, enclosure protection rating that tells you how protected it is from dust and water. Explosion-proof classification for hazardous areas, the actual physical size, and of course a unique serial number. It's really a treasure trove of information, a complete profile.
Wow, okay. That is a lot to take in, especially if you're just starting out. So here's where it gets, I think, really interesting. Let's zoom in on the 5 most representative, most critical items you'll find on pretty much every motor nameplate.
The core information.
Exactly. Let's call them the big 5. These really tell you the motor's core identity, especially helpful for our beginners listening in.
Okay, let's do it.
First up, let's talk about rated voltage and rated frequency. What exactly are these, and why are they so important for a motor to even work right?
Okay, think of them as the motor's fundamental dietary requirements. Rated voltage is the specific input voltage at which the motor is designed to operate safely and normally, delivering its intended power.
So the right food level, basically.
Precisely. If you give it a voltage that's too low, the motor will struggle. It might draw excessive current trying to compensate, and then it'll overheat.
And too high.
Too high. And you risk damaging the insulation, the windings, other components. It's kind of like trying to run a car on the wrong type of fuel. It just won't work as intended, and you could cause real damage.
Okay, so voltage matching is step 1. What about rated frequency? I know we hear about 50 hertz and 60 hertz being used in different places.
That's right, and frequency is just as vital. It dictates the speed at which the magnetic fields inside the motor switch back and forth. This directly affects the motor's rotational speed.
So it controls how fast it spins.
Primarily, yes. And globally, we mainly use either 50 hertz or 60 hertz. Now, here's something that might surprise beginners. If you try to use a 60 hertz motor in a region with a 50 hertz power supply, or the other way around.
Like if you moved equipment internationally.
Exactly. That mismatch can seriously affect the motor's speed. It'll run too fast or too slow. But maybe even worse, it can cause it to generate excessive heat, lots of extra heat. And that leads to substantial energy losses, and it drastically shortens the motor's life.
Wow. Okay, so it's not just a minor inconvenience.
Not at all. What's fascinating here is how these two, voltage and frequency, they are the absolute fundamental requirements. The basics for a motor to even begin to function as intended. They're like the basic operating instructions it needs to receive power correctly. Getting them wrong is pretty much a guaranteed path to trouble.
That's a really crucial point. So checking these two things, rated voltage and frequency, that really has to be the very first thing you do when you're setting up or operating a motor. It's non-negotiable, right? For safety and just making it work properly.
Absolutely non-negotiable. Neglecting it could quickly lead to some very expensive problems, or worse.
Okay. Next on our big five list, rated current. How can we understand this one in a simple way?
We can think of rated current maybe as the motor's body temperature. This is the normal operating current that flows through the motor when it's functioning as designed, doing its job without being under strain.
Like our normal 98.6 Fahrenheit or 37 Celsius.
Exactly. Just as a person has a normal body temp and a high fever signals a health problem, a current that's higher than the rated current, which we call an overcurrent, that signals a problem with the motor.
So an overcurrent is like a motor fever. Okay, I get that analogy. What happens if that fever goes unchecked, if it keeps running with too much current?
Excellent analogy. Well, if that fever persists, prolonged operation at overcurrent can cause the motor windings, the coils of wire inside, to overheat severely.
And heat is bad for wires.
Very bad. It leads to the breakdown of the insulation, which is critical for keeping the electrical conductors separated. Once that insulation fails, you can get a short circuit, more damage, and in really severe cases, even a fire. It's actually one of the most common ways motors fail prematurely.
Right, which is why careful monitoring and protective equipment are so vital, isn't it? Things like an overcurrent relay or OCR, I've heard of those.
Precisely. An OCR is specifically designed to detect these dangerous overcurrents. And then it takes action, like tripping a breaker or shutting off the motor to protect it and the whole system it's part of.
So it's like an automatic safety switch?
Kind of, yeah. An automatic alarm system that acts when the motor's fever gets too high. Ignoring this number on the nameplate, the rated current, it's a bit like ignoring a persistent cough. It could be a sign of something much worse brewing inside.
Okay, good advice. Moving on to number 3, rated output. For someone trying to understand, how powerful a motor is, what does this tell us?
This is the guaranteed muscle of the motor. Simple as that. It specifies the mechanical power the motor can actually deliver to do work.
Like horsepower in a car.
Exactly like horsepower in a car engine.
Yeah.
It's a very similar concept. Motor output is typically expressed in kilowatts, kilou, or horsepower, HP. And just for reference, 1 HP is approximately equal to 0.75 kilowatts. It's basically the motor's working capacity, its strength. Now, what's interesting to note, especially for those connecting the electrical dots, is that while simple electrical power often just considers voltage and current.
Right. PVI, basic formula.
Yeah, but for a motor's mechanical output power, things like efficiency and another factor called power factor must also be carefully taken into account in the calculations. It's a bit more complex than it first appears.
Ah, okay. So it's not a direct conversion.
Not quite. But for the beginner, the main takeaway is rated output equals the motor's guaranteed strength or muscle power.
Got it. So it's not just about how much electricity goes in, but how much actual physical work the motor can consistently put out. That's a key distinction.
Precisely.
Okay, number 4 on our essential list. Insulation class. This sounds critical. How does this relate to the motor's health and maybe its lifespan?
It absolutely relates. Insulation class tells you how well the motor handles the heat. Basically, when current flows through the motor's coils and its iron core, a significant amount of heat is generated. It's unavoidable.
Just physics.
Right. The insulation class indicates the motor's insulation performance level, how much heat that insulation can take before it starts to break down. It's usually shown as an alphabet letter on the nameplate, like B or F or H.
And why is this so important for lifespan?
Well, here's the really profound part. A motor's ability to either dissipate that heat or simply withstand it is probably the biggest single factor in determining its lifespan.
Wow, the biggest factor.
Arguably, yes. A good motor, ideally, should generate less heat in the first place, and its insulation needs to be robust enough to tolerate the heat it does generate over long periods. Higher resistance to temperature means a better insulation class.
So a higher letter usually means it can handle more heat.
Generally, yes. There are typically 7 different classes, represented by letters, and each one signifies a different level of temperature tolerance. This directly impacts how long your motor is likely to last, especially in a tough operating environment.
That makes perfect sense. Heat is the enemy, really. And this leads us right into our 5th critical item, temperature rise. How is this different from insulation class, and why is it important to keep an eye on?
Good question. While insulation class tells you the maximum temperature the insulation can withstand safely,
The limit.
right, the limit, temperature rise, on the other hand, refers to the actual increase in the motor's temperature above the ambient or surrounding air temperature when it's operating normally.
So how much hotter it gets than the room it's in.
Exactly. That increase happens because of internal losses, both electrical resistance losses in the windings and mechanical friction losses in bearings and things like that. These losses are converted into heat.
And that heat causes the motor's temperature to climb.
Correct. So it's all about managing that internal heat buildup.
I imagine too much temperature rise is definitely bad then.
Absolutely. Effective heat dissipation. How well the motor gets rid of that heat, maybe through cooling fins or a fan, is crucial to keep the motor operating within the allowed temperature range specified by its insulation class.
Right, stay below that limit.
And this raises an important point. It's not just about avoiding catastrophic overheating. It's more about finding that Goldilocks zone, where the temperature is just right for optimal performance and longevity.
Not too hot.
Right. Excessive motor temperature, even if it's slightly below the absolute limit, can dramatically reduce the lifespan of components like the coils and especially the bearings. It degrades the insulation over time, making it brittle, and that can eventually escalate into short circuits or fires.
Okay, but here's something surprising I read in the source material. Operating a motor when it's excessively cold can also cause problems. That seems counterintuitive.
It does seem counterintuitive, but it's true. While overheating is definitely the more common concern, operating a motor in really cold conditions can cause issues like internal moisture condensation when it warms up, or even freezing if there's moisture present.
Like condensation inside.
Yeah, or the grease in the bearings can become very thick and sluggish. This increases mechanical resistance, makes the motor work harder, and degrades performance. So it really is about striking that optimal balance, ensuring the motor operates in an environment that's neither too hot nor too cold for its design.
The Goldilocks zone for motors. I like that. So, okay, we've covered the big 5 from the nameplate, voltage, frequency, current, output, insulation, and temperature rise. What does this all mean when you're actually, say, picking out a motor for a specific task?
Right.
It's clearly not just about grabbing any motor off the shelf that looks about the right size. It's really about matching its characteristics, those things on the nameplate, to the job it needs to do and the environment it's going to live in.
That's a critical point, especially for beginners. The motor nameplate gives you that foundational knowledge, those absolute basics we just covered, the non-negotiables. But truly choosing the best motor for a specific application, that requires understanding the broader operational context and the environmental factors. It's definitely like picking a specialized tool you wouldn't use a hammer when you need a screwdriver. Right.
Right. Can you maybe give us a few examples of these broader factors, perhaps the most common ones that beginners might overlook, even after checking the big 5?
Certainly. Let's focus on a few key areas that really make a difference in the real world. First, think about the operating environment itself specifically. Things like the ambient temperature and how clean or dusty it is.
Where it's physically located.
Exactly. A motor designed for, say, a nice, cool, dry office environment might fail really quickly if you stick it in a hot, dusty factory, even if all the nameplate electrical specs seem to match. The nameplate's enclosure protection rating, sometimes called an IP rating, gives you a clue about dust and water resistance. But you still need to think about the actual conditions, like running a simple open-frame motor next to a furnace. Probably not a good idea, regardless of its voltage rating. It just won't be able to shed heat properly.
So durability and cooling in that specific spot matter hugely. That makes sense. What's another factor beginners should keep in mind?
Another crucial one is the type of load the motor will be driving. What's it actually connected to?
What kind of work is it doing?
Precisely. Is it something that needs to start and stop really frequently, like maybe a conveyor belt that indexes forward, stops indexes again? Or is it something that runs continuously for hours and hours, like a big ventilation fan?
Okay, different demands.
Very different. Or is it driving a really heavy piece of machinery, something with a lot of rotating mass, what we call a high inertia load, something that's really hard to get spinning or hard to stop once it's going?
Like a big flywheel or centrifuge.
Exactly. The nameplate might not explicitly say great for frequent starts or handles high inertia loads, but knowing the application helps you interpret those nameplate specs in context. A motor that has to overcome high inertia every time it starts, for instance, experiences much higher stresses and much higher inrush currents than one that just smoothly spins up a fan.
And that higher stress means more wear and tear if it's not designed for it.
Absolutely. If you pick a standard motor for a really demanding start-stop or high-inertia application, you're likely looking at quick wear, overheating during starts, and a much shorter life.
That's a great practical point. Starting can be the hardest part for a motor. Any other key considerations, especially for beginners wading into this?
Yes, one more that's becoming increasingly important, especially with modern control technology: power quality.
Power quality, you mean like stable voltage?
Partly, but it's more subtle than that. Many applications today use variable speed drives, or VFDs, to control motor speed efficiently. They're great for saving energy and providing precise control.
I see them everywhere now.
Right. But while they offer great flexibility, they can sometimes introduce, let's call it electrical noise, or distortion onto the power supply waveform. Technically, these are called harmonics.
Harmonics,
Now,
yeah.
these harmonics aren't always obvious if you just use a basic voltmeter, but they can silently cause extra heating inside the motor, effectively cooking it slowly from the inside, even if the average voltage and current readings look perfectly normal according to the nameplate.
Wow, so the power itself isn't clean.
Exactly. It can be dirty power, electrically speaking, and this might mean you need something called an inductive reactor, sometimes called a line reactor, installed between the VFD and the motor. It's essentially a specialized coil that helps smooth out the power flow, filter out those harmful harmonics, and protect both the motor and the drive itself.
So it's not just about the level of power like voltage, but the actual quality or shape of the power waveform.
You've got it. That's a really fascinating insight, isn't it? It goes way beyond just the basic numbers on the nameplate and forces you to think about the entire system: the power source, the controller, the motor, and the load, all interacting.
Yeah, it really highlights that the nameplate gives you that foundational knowledge, those essential specs.
Starting point.
But truly, choosing the best motor requires understanding these broader operational contexts and environmental factors, even subtle things like power quality that you might not immediately think of.
Absolutely right.
Okay, so we've peeled back the layers of the modal nameplate today. We've hopefully transformed what might seem like a cryptic code into a much clearer guide for using motors safely and effectively.
Making it make sense.
From understanding its basic power requirements, the voltage and frequency, to how it handles heat with insulation class and temperature rise, and even thinking about its current draw and output power, you now have a handle on the critical information that ensures a motor's health and longevity.
And hopefully this deep dive empowers you, our listener, with practical knowledge. It helps you not just to, see a nameplate, but to truly understand these machines that are the workhorses of our modern world.
Right. It's about being informed, making better choices when selecting or operating a motor, and maybe even spotting potential issues like signs of overheating or strain before they become big, expensive problems.
That understanding, especially approaching it from a beginner's perspective, but gaining that deeper insight, can save you time, money, and definitely help prevent hazards down the line.
So next time you see a motor, maybe it's in your washing machine, maybe a ceiling fan, or perhaps a really powerful piece of factory machinery, just pause for a moment. Think about its silent, unassuming nameplate.
A little middle tag.
Yeah, and maybe wonder, what other hidden IDs are there on the technology we use every single day, just waiting for us to uncover their secrets? What seemingly small detail, like a letter on a nameplate, might actually be vital to the bigger picture? Keep that curiosity alive.